Okay. Today we're going to have a look at the differentiation of trigonometric functions. Now, we've seen in the past how to differentiate normal functions such as x squared or x cubed or e to the power of x. And there are simple rules such as the power rule or the quotient rule or the product rule or the chain rule that can help us differentiate these functions. The differentiation of sine, cos and tan though is not as straightforward because yes, they are functions, but they don't act in the same way as other functions because we've got this whole sine or cos or tan thing rather than just having x squared or x cubed. All of the rules of differentiation, even though they're quite easy, all of them come from first principles. So the only way we can figure out how to differentiate these is to follow first principles. F of x plus h minus f of x on h. Now, using our compound angle formula, we can easily expand this and get sine of x cos of h plus sine of h cos of x minus sine of x over h. And again, I've forgotten my limit there. That's bad of me. Now, let's take out a factor of sine of x, and we might write it as two separate fractions. So we're going to have sine of x outside of cos of h minus 1 over h, plus we've still got sine of h cos of x over h. So all I've done there is split it up into two fractions and taken out a factor of sine of x there. We're allowed to split things like this up into two fractions because we know from basic primary school maths, I can add two fractions with the same denominator. So since I can add two fractions of the same denominator, I can also pull them apart with the same denominator. Now, if we started to substitute, say, 0 into this first fraction, well, cos of 0 is 1. So since cos of 0 is 1, then 1 minus 1 is 0. So this whole part of the inequality goes away. Now, in a similar way, we've got the limit as h approaches 0. And we're trying to figure out what sine of h cos of x on h is. Now, we're not allowed to just go and substitute in 0 at this point because everything is multiplied by everything. So if we just substitute in 0 here, then that means we're substituting in 0 here, and we're not allowed to divide by 0. So we've got a little bit of a problem here. We can't at the moment calculate the limit as sine of h cos of x on h approaches 0. We could, though, say that this is the limit as h approaches 0 of sine of h on h times by the limit as h approaches 0 of cos of x. Now, the limit as h approaches 0 of cos of x is just cos of x because there's no h in there. So we can get rid of that and state this. The limit as h approaches 0 of sine of h on h times by cos of x. Again, another problem here because we don't know what the limit as h approaches 0 of sine of h on h is. So we're going to try and calculate that, and we're going to use the unit circle to do this. So if we draw a unit circle, of course a unit circle has a radius of 1. And we're going to draw a few things on this unit circle, and it's going to come up with a cute little inequality, which is known as the squeeze theorem. So, and I haven't done this proof in quite a while, so I'm just going off my head, so hopefully I get it right. The squeeze theorem is something that helps us calculate the limit as h approaches 0 of sine of h on h. We're going to draw a few triangles in this unit circle. I might start by drawing this triangle here, and then I also might extend that triangle up like that and extend that there. And we're going to say that this triangle has an angle with the positive x-axis of x radians. Now we're going to come up with some sort of inequality here, and we're going to do that by considering the area of each of these triangles, the area of this sector, and the area of this triangle. And what we're going to do, if I call this area 1, the sector area 2, and the larger triangle area 3, we know that area 1 has to be less than the area of the sector, which has to be less than the area of the bigger triangle. And that is going to be the basis of our proof here. So let's find the area of the smaller triangle here, so this triangle here. We know that the area of a triangle is a half the base times by the height. So the base of this triangle, since it's a unit circle, is 1. So a half times by 1 times by. The height of this triangle is this thing right here in red, h. We're thinking, okay, how can I find the height of this triangle? Well, I know this is a unit circle, so this is a radius of 1. And the angle of this triangle is x. We've defined that this triangle and that this sector of this circle has an angle of x. And that's because this can represent any angle within the triangle. So we're just going to call it x. Now, using right-angled trig, sine of x is opposite h over hypotenuse 1. So the height is sine of x. So that means the area of this triangle is sine of x over 2. We might start constructing this inequality. Sine of x on 2 is going to be the smallest in our inequality, and we're going to have three things in our inequality. Here we're going to have the sector, and here we're going to have the larger triangle. Let's find the area of the sector now. Now, we know that the area of a circle is pi r squared, and the radius of this circle is 1. So the area of this circle is pi. However, we've only got x radians, x degrees worth of this circle. So we're going to times it by x degrees, x radians, I should say, over the total of 2 pi radians in a circle. And that gets us that the area of this sector is x on 2. And I'm pretty sure that's an advanced formula. The area of a segment is 1 over the angle over 2. Yeah, that's one of the formulas. But I've just proven it there. So the area of that sector is x over 2. Let's add that into here. X over 2. Okay, now we're going to find the area of the larger triangle. So this larger triangle here is this one here. So we know that the area of a triangle is half the base times the height. Now again, that this is a unit circle, so the base of this triangle is 1. So a half times 1 times pi. The height of this triangle is a bit more tricky because we don't know that what this hypotenuse is. We know that this part is, this much is 1, but I don't know what the rest of this is. I do know, however, that its base is 1. If we call this, if I get rid of this height so it's not confusing, if we call this h for height, well, we're tan because we've got an opposite and adjacent. So tan of x, that's my angle, is h on 1. So the height of that triangle is tan of x. So the area of this larger triangle is a half tan of x on 2. So let's recap what we've just done. We've calculated that the area of this triangle is sine of x over 2. Then we've found that the area of this sector is x on 2. And the area of that sector has to be larger than sine of x on 2 because we're adding this bit here. Then we're finding the area of this largest triangle, and we've found it's tan of x over 2. And that has to be larger than both of them. Look in your diagram, we can see it's larger, and it also includes that. So this is an inequality here, and we're going to try and rearrange it to get what we're after. We're trying to prove that sine of x on x, as x approaches 1, is 1. Now we can multiply everything here by 2. And we want sine of x on x. So what we might do here is divide everything by sine of x. 1 is less than x on sine of x is less than, now tan of x, well, tan is sine of x on cos of x. So if you get sine of x on cos of x and put it over sine of x, you're going to get 1 on cos of x, or sec x. We're still not quite, though, where we're after. We want sine of x on x, and from that I'm thinking we need to take the reciprocal of everything. Let's think, though, what happens when I take the reciprocal of an inequality. Let's say 2 is less than 5, which is less than 6. If we take the reciprocal, 1 on 2, 1 on 5, and 1 on 6, well, 1 on 2 is greater than 1/5, and 1/5 is greater than 1/6. So when I take the reciprocal of an inequality, it swaps all of them. So the reciprocal of 1 is 1. The reciprocal of sine of x on sine of x is sine of x on x. And the reciprocal of 1 on x is cos of x. Now we're taking the limit as x approaches 0 of this. And if I substitute in, I can't substitute in 0 into 1. Let's leave this alone for a second. If I substitute in 0 into cos of x, I get 1. So, this is what we call the squeeze theorem. And it's telling us that the limit as x approaches 0 of sine of x on x is squeezed between 1 and 1. But if something is squeezed between 1 and 1, then it's just equal to 1. So therefore the limit as x approaches 0, not h, the limit as x approaches 0 of sine of x on x is equal to 1. So we've just proven that that limit is true. Let's get back to why on earth we were figuring out that limit. We were trying to differentiate sine of x. So we used first principles and we were trying to figure out the differentiation of sine of x. Now we've just proven that this limit is a 1. So 1 times cos of x. So therefore the differentiation of sine of x is cos of x. Now we can do a very similar proof to prove these following qualities. The differentiation of sine of x is cos of x. The differentiation of cos of x is minus sine of x. I'm not going to prove that, but you can prove it the same way. And the differentiation of tan of x is sec squared of x. Now that's something I hope that you'll prove in advanced. You just need to use the quotient rule of sine of x on cos of x and differentiate them both separately. These are our basic trigonometric differentials. The form that we're going to focus on are these ones here. The differentiation of cos, or we might start with sine. Sine of f of x is f dash of x cos of x. The differentiation of cos of x, or cos of f of x, is f dash of x sine of x, but we've got to put a minus out the front. And the differentiation of tan of f of x is f dash of x sec squared of x. Those are the formulas that we need to have had memorized for trigonometric differentiation. We'll do 3 examples, and then we'll finish. Number 1, we're going to find the differentiation of sine of x squared. Well, the formula says that we differentiate what's in the brackets 2x and times it by cos x. Number 2, the differentiation of cos of x cubed plus x. Well, again, the formula tells us we differentiate what's in the brackets, 3x squared plus 1, times it by sine of x, and put a minus out the front. Number 3, let's differentiate tan of 3x. Well, we differentiate what's inside the brackets, 3, and then we multiply it by sec squared of, actually I've made a mistake there, sec squared of 3x. We're keeping this original function the same here. I might do another one just to consolidate that. The differentiation of sine of 5x squared. We differentiate what's in the brackets, so 10x, and then multiply that by cos of what's in the brackets, 5x squared. Okay, that's differentiation of trig. Thank you.